Hello, this is Brian Washburn. I'd like to talk about Lagrangian mechanics. Okay, so Lagrangian mechanics is a formalism mechanics that's based on a least action principle, and that principle is called Hamilton's principle. Okay, and the idea is this: the Hamilton's principle says that consider I have a solution to a mechanical system. I'm going to call that a path. X is a function of time. Okay, the actual solution or actual path that a particle follows between 2 points between a time interval is such that that solution minimizes something called an action integral. And the actual integral is the integral from times t1 to t2 of a function L called the Lagrangian, where Lagrange is the kinetic energy minus potential energy. So the actual solution to a mechanical system will make this thing a stationary. And so then how do you find that actual path? X is a function of time. What you do is we use methods from the calculus of variations. Okay, and we can solve for that. So from our discussions of the calculus of variations, what we're going to do is we're going to solve for not a path X is a function of time. We're going to consider what I call a generalized coordinate. A generalized coordinate is a general path. That path is going to call that QT. And QT might be, in general, might be X, Y, Z. It could be even angle. Okay. And associated with that QT are called generalized coordinates, or also called generalized velocities. Okay, those are the Q dots. All right. So what we want to do is we want to minimize the action integral of the Lagrangian, which is t minus u. And how do we do that? Well, what we do is we solve the Euler-Lagrange equation for Q as a function of time. So in the end, we're going to solve this equation here. That's going to give us a second order differential equation, which we still need to solve. So how does a problem in Lagrangian mechanics look? So let's take a look at a simple problem, or we'll look at the simple pendulum. Now here's an example of a simple pendulum. What I have is I have the pendulum of mass m, length string L, okay, and it moves in the xy plane where x is pointing down, y is horizontal. When I consider problems in Lagrangian mechanics, I do not have to consider forces. All I have to do is consider the kinetic and potential energies, because in the end I will get the Lagrangian. However, I have to write down what are called equations of constraint. And you think about this particle here, well, it moves in xy plane, but it can't move arbitrary in x and y. It moves along an arc of a circle. So an equation of constraint is x squared y squared equals L squared. Okay. Now, one thing you should not forget is that that equation of constraint is due to a fact there is a tension in the string. So in general, anytime I have an equation of constraint, that equation of constraint is due to a force. Okay, even though it doesn't show explicitly in Lagrangian mechanics. Well, here it doesn't, but there's always a force. For every force is an equation of constraint. Okay, once I have that, I can write down the kinetic and potential energies. The kinetic energies is 1/2 mv squared. Okay, but again, I have to break up in x and y components. And the potential energy, again, only meaningful, I have to define the zero potential energy. So I define it at this point here, where the length of the string, where this bob is all the way down here. That gives me kinetic and potential energies. Now notice that my kinetic and potential energies are in terms of both x and y, or x dot and y dot. But really, this is one-dimensional motion. And I can always relate the motion of x to y to an angle theta. Now really, this is one-dimensional motion. That means there's 1 degree of freedom. Okay. In the end, that's going to say we're going to have one generalized component, a generalized coordinate. So this delta here, that's going to be our q. Okay. And so in the end, when we do problems, you say, well, what are the generalized coordinates going to be? Well, for every degree of freedom in a problem, I'm going to have a generalized coordinate. Because I can always relate x and y, the Cartesian coordinates, using these equations here, this equation here and this equation here, to the generalized coordinate. So it's a one-dimensional problem. Again, no forces, so we have to consider equations of constraint, kinetic energy, potential energy, and then finally, what is my generalized coordinate going to be? It's going to be a degree of freedom. All right? Now, let's look at this problem in more general context. So here I want to look at Lagrangian mechanics in a very general context, and say I have a system of particles, okay? And say I have n particles in three-dimensional space, and there are m equations of constraint to act on it. So just like we did before, we said, okay, I have one particle. Before I had one particle, and I have one equation constraint. Okay, but that particle can move in 3 dimensions. The big question when doing Lagrangian mechanics is, how many generalized coordinates are going to have, and what are they going to be? Well, in general, they're going to be the degrees of freedom of the particle can have. So I'm going to say I'm going to call S. S is going to be called the number of generalized coordinates. It's going to be, 3 times the number of particles minus the degrees of freedom. Okay, because remember that the equation is constrained. The equation is constrained, constrain it, and that's going to reduce the degrees of freedom. So for every particle, I have n particles, and they can move in 3 dimensions. So 3 times n is the number of degrees of freedom. But then I constrain them by m constraints, and that gives me the number of generalized. That gives me s, the number of generalized coordinates. So all my q sub. So again, q sub j, where j is an index that goes from 1, 2, all the way to s. So these are my generalized coordinates. Okay. However, again, what's really important, the generalized coordinates may not be Cartesian coordinates. They may be angles. They could be something very, very weird. I have to have relationships between the generalized coordinates and the Cartesian coordinates. And so here, x are my Cartesian coordinates, okay? And x has 2 indices, alpha and I. Alpha is the particle, so alpha goes from 1 to 2 to n. That's the number of particles. I goes 1, 2, 3. So x1 equals x, x2 equals y, and x3 equals z. Okay. Now, these Cartesian coordinates, in general, may be functions of not just q dot j's, and time as well, depending on the problem. Okay. But again, what these guys are, they're relationships. They're relations between the Cartesian coordinates and the generalized coordinates. And we're going to need them because when we calculate the kinetic energy and the potential energy, we're going to first use Cartesian coordinates and then relate it to generalized coordinates. And then finally, I have equations of constraint. In general, those equations of constraint can be written as f is some function of the Cartesian coordinates and possibly time equals 0, where k is an index from 1 to 2 all the way to m. Okay, so that's my system in general. It seems complicated, all right, but it's really good to know this because Lagrangian mechanics is very method-based. So if you just follow the procedure, you can solve these problems pretty easily. Okay, all right. Now let's talk about the kinetic and potential energies. Okay, so in the end, I'm going to get an Euler-Lagrange equation for each degree of freedom. So for each qj, I'm going to have, for each degree of freedom, I'm going to have a generalized coordinate. I'm going to have a Euler-Lagrange equation to solve for that. All right, where the Lagrangian is going to be a function of q dot, and possibly time as well, explicitly. All right. Now, how do I get the kinetic energy? Well, the kinetic energy I'm just going to get from the Cartesian coordinates. In fact, it will always be. So again, I have to sum over the particles and the x hat, x dot, y dot, and z dot for all those. So this basically is the Cartesian representation of that. Looks a little complicated, but it's actually fairly straightforward. However, again, the problem here is that, hey, wait a minute. My Lagrange is not in terms of xi. It's in terms of qj. And so I got to get this guy into terms of q's, not x's. Now that depends on the problem on how you do it. The way you're going to do it is you're going to use these expressions x that relate to the general coordinates q. And in general, it's going to look something like this, where this mass is given by this expression here. Now, in the end, this is going to be pretty easy. We're not ever going to see this. For some problems, we might need to do something like this, but okay, it's going to be pretty easy. Don't worry about it. All right. Okay. Potential energy. Now, potential energy just should depend on x. Okay. However, you got to be really careful here. That x may be a function of q dot, and j. Okay. Now you may say, well, how the heck when is a potential energy should never depend on time? Well, in one coordinate system, you may have a fixed coordinate system, but then you might be doing things in a moving coordinate system, and so the potential energy may depend on time. Okay. Now, for conservative systems, u is just going to be a function of q by itself, no time or velocity. Now, things get even more complicated. In the end, we may define a fictitious potential energy that might depend on speed. It might depend on time as well. Okay, we'll see problems like that. All right. So finally, how do you choose the generalized coordinates? It comes through experience, but actually, what you need to do is you need to first calculate. Roughly, you have to calculate the number of generalized coordinates. So you think about, okay, number of particles times 3 minus the number of constraints. That gives me the number of generalized coordinates. Really, S is a measure of the degrees of freedom to a problem. So if you think, okay, for every degree of freedom I have in a problem, if it's a one-dimensional problem, I'm going to have one generalized coordinate. If it's a two-dimensional problem, I'm going to have two generalized coordinates. But in the end, your generalized coordinates must describe three things: motion about the center mass, rotations about the center mass, and any motion of the constrained equations. The equations are constrained. Okay. So that's a lot of stuff. That covers things very general. What's really important is, and really the way we're going to learn how to do this is to see examples. So I'm going to do a simple example here, and we'll do much more complicated examples in class. So let's look at a simple example. So here's my simple example, that of a simple pendulum. Now let's kind of go through this list and figure out, all right, let's try to figure out, what are my equations of constraint? What are my relationships between the Cartesian coordinates and generalized coordinates, and how many generalized coordinates I'm going to get? So how many particles do I have? I have one particle, so n equals 1. How many Cartesian coordinates I have? Well, technically, for one particle, it can move in 3 dimensions. Everything's 3 dimensions, so I have 3 times 1 or 3, x, y, and z. What are my equations of constraint? Well, there are 2. First of all, the particle does not move in the z direction, it only moves in xy plane. So one equation of constraint is z is equal to 0. Then the other equation constraint is x squared plus y squared equals L squared and moves in the xy plane. So m is the number of equations of constraint. How many generalized coordinates are going to be? Well, this is one-dimensional motion, so I expect 1. Well, 3 times 1 minus 2. Again, 3 times 1 is the number of Cartesian coordinates. 2 is the number of equations of constraint. This guy and that guy, that's 1. So my Q is this phi. Now I have to have relationships between the Cartesian coordinates and the generalized coordinates. That's these: x is equal to L cosine, okay, right angled, y is equal to L sine, and z is equal to 0. Great. Now I have those functions. Now the next step to do is calculate the kinetic energy, potential energy, and the Lagrangian. Okay. Now the kinetic energy is 1/2 m v in x component squared, or v squared, which is x dot squared plus y dot squared. I basically take the derivative of this, stick it into there, and I get this. Now that's really important, because now I have the expression of the kinetic energy in terms of my generalized coordinate. I do not want the kinetic energy to be in terms of my Cartesian coordinates. I want it all in terms of generalized coordinates. Potential energy. mg, the height. The height is going to be L minus x, and I can just say that's just going to be mg 1 minus cosine. And again, I have in terms of my generalized coordinate. Lagrangian is just the difference between the two. Okay, now what's the next step? Next step is now I have Lagrangian. I take derivatives and use the Euler-Lagrange equation. Let's look at that. Okay, so since I only have one generalized coordinate, I only have one Euler-Lagrange equation, and that's this guy here. Partial L respect to phi minus the complete derivative ddt of partial L respect to phi dot equals 0. Now, you have to look at my, I should have wrote this, but take a look at my, notice that my Lagrangian is a function of phi dot and phi. One thing you're going to learn that's really important is recognize the functionality of the Lagrange in respect to the generalized velocity and generalized speed. Okay, now notice that, generalized velocity and generalized coordinate. Notice that they're both in here. Phi and phi dot are both in here. All right. If I take the partial of L respect to phi, this guy is a constant. That goes that's a 0. This times that's a constant. I'm just going to get, I get a plus sign, but the derivative of cosine is a minus sign, and I get that. Now I take the partial of L respect to phi dot. The only thing that has a phi dot is this term here. And so I take 2 times 1/2 ml squared. Okay. I forgot the square there. Yeah, I forgot a square there. So there should be a square there. Just checking that. Okay. And then, so then what I do, okay, so then I get that, then I take the time derivative of that. Well, the only thing that depends on time is the phi, so I get phi double dot. Now what I do is I stick this into this differential equation here where I have a square here, okay, and I divide by L, I divide, and I'm going to get phi double dot is equal to minus GL over L sine of phi. Well, that's all we got before for a simple pendulum. So we got the same dang equation of motion. Now you might say, well, it was a lot easier to use Newton's equations, F equals ma, to get this than what I just did here. And that's actually true. However, the problem we're going to do in class is this problem here. So say I take a pendulum, okay, and I take its base, and I accelerate its base at a constant acceleration. Find the equations of motion for that. That's not a simple problem using F equals ma, but it's not going to be too bad using Lagrangian mechanics. Okay, so the best way to learn Lagrangian mechanics is this. We're going to do a lot of examples, both in the homework and in class, and you'll learn how to do it. We'll see you later. Bye-bye.